Apologize for that. So next we'll have Randy Gross addressing attack vectors in IoT for AI models. Randy has held several C-level and VP-level positions at IBM and Dell in the past. He now leads engineering and data management at SparkPredict, bringing the benefits of AI to the industrial applications. Randy holds a master's degree from the University of Texas in Austin and a master's in technology management from MIT, as well as bachelor degree in electrical engineering from Kansas State. Please welcome Randy.
Thank you, Nadine. Thank you, everyone. I'm excited to be here to share a little bit of our experience, and like Nadine said, we are focused in the industrial IoT space, but I think you'll see a lot of the issues I bring up are applicable to smart cities or vehicle-to-vehicle type applications that you guys have been talking about at this conference. So before I talk about what's unique about AI models and the attack vectors that come in, I'm going to give you a very quick high-level tutorial about how AI models are developed. There's lots of different techniques for it. Of course, the popular one today is neural networks, and I'm going to focus on that, but a lot of the issues I bring up are common to other techniques as well. Of course, AI models are software, so some of the attack vectors are fairly traditional software attack vectors, so I'll talk a little bit about that, but then spend most of the time talking about what are attack vectors that are unique to AI models that aren't in typical software. So first, AI modeling is a very different approach than traditional software. In traditional software, you come up with an algorithm, you write it down, you provide inputs, and you get the answers out at the end. For AI models, it's different. You start with the answers for the data that you have, and you use that to develop the algorithm. So it kind of turns this on its head. In a lot of ways, it's similar to how humans learn. You learned how to do multiplication from multiplication tables, which is basically a set of data of two numbers that are being multiplied together with the answers that you learned. Same way that a neural network model will learn how to do multiplication. Now, what you want it to be able to do is learn things it hasn't seen before. So in this case, you would give it 70% of the multiplication table and expect it to be able to find the answers to the other 30% that it hadn't seen before. So you really want it to learn something about data it hasn't seen as well as data that it has seen. So that's kind of one way to think about it being different from traditional programming. Now, the way that this gets encoded in a neural network is you basically have a graph of perceptrons that are all interconnected to each other. And the inputs to those perceptrons all are multiplied by individual weights. So each input has a different weight. Those are typically summed together and then presented to a nonlinear activation function that determines what is sent to the next layer of the network. That means the way that this information that it's learned is described is all a bunch of floating point numbers, and a graph of those interconnections. So it's to a human being, while at least decently written code is something a human being can kind of sit down and figure out what it's trying to do and what its algorithm is and how it will behave. With a neural network, it's very difficult, if not impossible, to figure that out from just this list of essentially random weights, if you will. So it's a very different kind of problem to deal with. Also, these models, as they exist today, are typically very brittle. You may have heard about the big accomplishment in which Google's DeepMind organization has trained a neural network model called AlphaGo to play the ancient game of Go, which is this 19 by 19 grid with black and white stones on it. Thought that never be able to equal humans. Well, they now can routinely beat human beings with this fantastic model that they developed, and which is all great. But take that same model and ask it to play tic-tac-toe, and it would fail miserably. So these are very good. They're like idiot savants, very good in the domain that they're trained in, and terrible once you step very far from where they were trained. So first, let's talk about traditional attacks from software. Again, AI models are based on software, so you have to worry about those kind of attack vectors. And today, attack vectors, malware go after bugs that are in the software, cause it to take control of your machine or steal your data, and they leverage things like macros in Word documents or images in PDFs, or even sometimes the fonts that are in your documents, or the operating system or networking stack. There's lots of different places that they can go in, and they tend to attack those things that are common on your PCs. The same kind of thing can apply to AI models. So again, if machine learning libraries have bugs in them too, and if I know that there's a bug in a machine learning language, I could craft a model and some input data that would cause that buffer overflow or whatever that would allow me to take over the machine. That's obviously easier to do if I can control the model and the inputs. But the bigger problem today is most people don't have TensorFlow or some other machine language libraries, machine learning libraries sitting on their PC. So it's not a very attractive attack vector today for a software perspective, because it's much easier to go after Word or Adobe Reader, etc. Now, the good news on the other side is that AI can actually help with this malware problem. So today, most malware techniques rely on having a lot of experts that are looking for the new threats that come out, develop a signature for those, send those out to your endpoints, and then your endpoints look for those signatures. The problem is, between the time that the malware is released and the signatures are released, everybody's endpoints are vulnerable to attack. What's nice since malware tends to have some characteristics that are kind of independent of each particular attack, you can actually use artificial intelligence to learn what malware looks like and be able to detect it basically day zero when no human has actually identified it before. And at SparkCognition, we have a product called Deep Armor that is exactly focused on that. If you can see the chart that's on here, there's a little green line at the top, and every day we download the newest malware that's been discovered out in the wild and run our model about it, and we run it against all of the other competitive malware detection algorithms that are out there. And you can see we're bumping along in the high 90% of being able to detect 0 days, where the performance of all of the competitors is quite varied depending on the type of malware. So good news is that AI can really help detect these 0 days and protect you from day zero. So now let's talk about how AI models have unique attack vectors. So let's start first with the training. As remember, the algorithms that are in the neural network comes from the training data that you give it. So it'll learn whatever you give it. And so anything that maliciously goes in and modifies the training data can cause it to learn the wrong things. So an example of, again, an application that we have at SparkCognition, we're helping one of our customers identify objects in video. In this case, trying to identify different types of ships. And this, all the images are labeled as to this type. It's labeled as a landing ship tank, and you end up training labeling a whole bunch of different data in order to train the model. Now, if somebody were to come in and change the labels in our training data, then you would see that all of a sudden this ship would be labeled as a jet ski. And if we didn't detect that somebody had modified that training data, then our models would actually be learning the wrong things. And it's really difficult, like I said, because the models themselves are just floating point numbers. It's hard to see that you've mistrained your model based on training data that's been compromised. Now, in reality, you can lock down your training data just like you lock down everything else, and hopefully that's not a common occurrence that somebody can go in and do that. What's actually a bigger problem typically is you unintentionally have polluted or biased training data. So an example, again, this was a couple of years ago, not involved with SparkCognition, but the U.S. Army had developed a model that was able to identify dummy tanks from real tanks. And it was in all the testing, it was beating humans very significantly in its ability to do that. So they were very excited about it. They take it out in the field and try it, and it failed miserably. And it took them a little while to figure this out because neural nets are hard to figure out. But they eventually realized that when the people that were asked to go create the training data, they went out and took pictures of the dummy tanks in the morning and the real tanks in the afternoon. And so what the model actually learned wasn't dummy tanks from real tanks. It learned morning from afternoon, which is not what they wanted. Just was reading an article this morning about Amazon had trained a model to help them sort through their resumes for job applicants, and they've had to cancel that because it turned out it was biased against females because their past training data was so heavily weighted to males, right? So it's, the polluted training data doesn't have to be malicious. It can be unintentional as well. Another source of potential training data issues is if you're crowdsourcing your inputs. That's really helpful if you can get people help labeling your training data sets. And one common example of this that you probably all have participated in is spam filters. So every time you mark something as spam, that goes back to the spam filter and as a false negative, and they use that to retrain their spam filters and make them better. Well, that works well as long as somebody like me who's wanting to get less spam and I'm only marking stuff that really is spam. But if you're a malicious person, you can be marking good emails as spam and causing all kinds of havoc. And so a lot of these spam filter companies have to actually have AI models that detect malicious reporting of spam as an example of trying to avoid polluted training data. Another attack vector is, like I said, models learn what they've seen, and when you show them something they haven't seen, you can often get very unpredictable results. Top example here, you can see the stop sign. There was a university that had, one of the professors there had his students train models that were trying to recognize traffic signs, right, which is an important application, obviously, for autonomous vehicles. And his professor in the next office decided to troll him, and he went outside the office there. And I don't know if you can see it. There's a little yellow sticky note that he put on that stop sign just below the letters there. And that model now has a very high confidence this stop sign is actually a speed limit sign, which of course would be a bad thing if this was an autonomous vehicle. But this can even be more subtle. As you can see, here's another example. This was actually from a model that was trained by Google themselves by just making a few modifications to the pixels that you and I can't even tell are there. It's now thinks this turtle is a rifle. And so it's, this is all a little bit humorous, but if you start getting to the point where autonomous action is being taken based on the outputs of these models, blowing through a stop sign for an autonomous car because you think it's a speed limit sign, or if this was a drone who thought this turtle was a rifle and decided to blow it up, those would all be bad things that happen when you have autonomous action and don't have a human in the loop. So a couple of examples. I'll do a consumer one, and then I'll do an industrial IoT one. This is a couple of things from an ad from a consumer security webcam. They've got the capability to learn who is supposed to be in your house most of the time, your family members, your maid, whatever, your animals, so that anytime something different shows up, it sends alert. That's obviously a lot better than just strict motion detectors, right? So that's really attractive. And of course, if you're just a standard burglar who doesn't know anything about this, you're going to probably get caught and set off an alert. However, if I'm really want to break into your house, and I know you have one of these cameras, and I can get pictures of your family members and what they wear and all that, I can probably put on the right clothes and maybe put on a mask and fool this system, right? Because again, it's something that it hasn't seen before, and it's not expecting somebody to try to disguise themselves. let's go to an industrial IoT example. This is an example from one of our customers at SparkCognition. This is a natural gas combustion turbine. Think of these as jet engines that are the size of a jet. They're hundreds of millions of dollars. They take air, compress them through these blades, and then you can see where the natural gas is injected and creates power. And these things have literally thousands of sensors on them to try to detect how well it's performing, try to detect things before they fail, because obviously with all this energy and power, bad things happen. You can actually have these things blow up and people get killed. I mean, so it's a very, not to mention just the lost, just the lost downtime and revenue that you get. So in this particular example, our customer bought the first 3 units off of a production line, and you saw those blades that are on the front are actually held in place by a retaining key. Now, obviously, the blades being in front, if something happens to them, that blade comes loose. It's going to go all the way through and basically destroy the machine. Well, it turned out there was a manufacturing and design flaw in these machines because they were the first ones on the line. Nobody knew about it because they were the first machines that came out. And it turns out that one of the retaining keys came loose, and this blade now started walking forward. And you can see that it's starting to hit parts of the machine, heating things up, causing some vibrations. But the temperature rise and the vibration rises were not enough for any of the traditional mechanisms to detect the fact that there was a problem here. And our technology was able to do that. I'll show that here in a second. But clearly, if this had gone on to complete failure, it would have literally been hundreds of millions of dollars of repair and lost revenue. So our SparkPredict product uses that capability that I talked about, that machine learning models don't know what to do with data they haven't seen before. Well, you can use an unsupervised technique like that to basically train it on when everything's normal. So it learns what normal looks like. It can put it in a bunch of different modes, and that's what you see on these green and blue bubbles that are on this chart are the normal operating modes of the turbine. But when something shows up that doesn't fit what it's seen before, it flags it as an anomaly. And you can see those are the purple clusters that are on here. And in this case, that vibration and temperature rise was just enough to be different enough to cause us to detect an anomaly. And we indicated that the reason we're calling it an anomaly is the vibration and temperature in this particular part of the turbine is bad, and therefore they were able to go out and fix it before it failed. So obviously extremely valuable. So the question is, how does this expose us from an attack perspective? So in this particular example, obviously there was a human in the loop. Humans looked at this, decided to go see what was wrong and fix it. But imagine a scenario where we get to the point where these plants are automated, and when they see something that's out of whack, they shut down the power subsystem or whatever. What that means is that an attacker doesn't have to go in and put a virus in your software or do anything to your software. They can attack the sensors. And by changing the values coming into the sensors, they can make the model think it's operating in an anomalous state and shut everything down, which is obviously a bad thing. Now, on the other hand, AI models can actually help detect software attacks that are trying to hurt your plant. So if all of you remember the Stuxnet attack on the Iranian uranium centrifuges, where they were able to get Stuxnet onto the controllers and basically make the controllers cause the centrifuges to destroy themselves. And they did it very subtly so that none of the alarm systems went off, just a lot like this walking blade that I talked about. None of the normal sensors, monitoring systems detected there was a problem until the centrifuges started blowing up. However, if they had been running SparkPredict on those centrifuges, they would have gotten an anomaly and been able to actually find a software breach that was causing that problem. And then a final way that neural networks can be compromised is by sticking in backdoors into the models. You know, you can basically go in there again because of everything is just weights and neural network connections. It's very hard to detect these, but you can go in. This is an example that's used a lot in machine learning, which is a data set of hand-drawn numbers, and the whole idea is to classify what number it is. It's a fairly simple problem. So in this case, obviously, these are sevens. But you can very easily put in some malicious neural network perceptrons that if they detect, for example, a single pixel of a certain color at a certain location on the screen, that it should report whatever answer you want it to. In this case, in the paper that's cited here, they had it always given 8 whenever it saw this. Or you can be a little more sophisticated and have to have a pattern that has to be recognized or whatever. But the point is, whatever you hide in there, then you can know that you have a compromised classifier and make it say whatever you've programmed it to do. While it's obviously difficult sometimes to detect backdoors that are written in standard open source programs that you pick up, detecting backdoor neurons is nearly impossible to do from looking at just the weights and activation functions. And another scary thing about this is a common practice in the field is not necessarily to start from a clean model yourselves. For example, if an example where we had the model that had been trained for U.S. traffic signs, and I needed to now create a model that recognized traffic signs in the UK instead. A typical practice would be to go pick up that model that had already learned US traffic signs and just now present it with UK traffic signs and just have it learn the differences, and you can train it faster, you don't need as much training data, and it's a very common technique. But what I don't know is, did the model that I'm doing transfer learning on, which is what that's called, if it had a malicious backdoor in it, I've now brought that into my UK traffic sign model as well. And so that's, again, a potential way for this stuff to propagate in much the same way that a virus can propagate in a computer system. So to kind of wrap things up and then open up some stuff for questions, so how do you avoid these problems? Obviously the first piece of it, since this is software, you got to use all the same common software, safe software techniques that you can, avoiding programming errors. Make sure you use things like deep armor to detect 0 days, those kind of things. But for artificial intelligence models, the training data is really the key piece there. First of all, make sure that you know the source of your training data, that it's not biased, and that it hasn't been modified, and keep it secure so it doesn't get modified. For being more robust to out-of-sample kinds of attacks, take the data you have and add noise to it, rotate it, do whatever you can to create additional slight variants of the data that you have so that it is more robust and less sensitive to out-of-sample training. And then, of course, if this model is going to be used to take autonomous action that has significant implications, like it's going to make a financial transaction, or it's going to shut something down, or something that has significant consequences, you really have to train it and test it very significantly to make sure that you know how it's going to perform in these unusual situations. And finally, if you are planning to use any third-party existing models or anything, make sure you know the provenance of that and make sure that it can't contain any backdoors. So that's really a quick run-through of some of the things to think about when it comes to artificial intelligence models and how they can be attacked. And like I said, these same kind of attacks would apply to a smart city or vehicle-to-vehicle types of communications for autonomous vehicles, et cetera. The problems are the same. So with that, I will open it up to any questions. Yes?
One question regarding that backdoor neuron problem. So, for example, you're downloading some Paris model like page 5, right?
Right.
Download it. So can, the model provided, they just simply apply a signature or hash to that original model. So then when you're downloading, you do a verification, then this backdoor neuron will be resolved.
Well, certainly if you can make sure that it hasn't been modified from the version that's on the web. However, if that original version had a backdoor already put into it, if the source of that model is a trusted source and didn't do that, having a hash on it would work well. Exactly. Yeah.
One more question.
Yes.
So for that turbine example, how much data was used to train?
We trained on about 2 years worth of data. Yeah.
And how long?
It took us, that was one of our first ones, so we actually had to go through a bunch of different modeling techniques before we came up with the one, but in fact, I just got an email. I was saying that we just trained another combustion turbine model in 3 days from getting data with 2 years worth of data on it. So, but for something like a combustion turbine, it's important to get, if you're trying to determine normal states, you really need to get a full year's worth of data just so that you know all of the seasonal, because how they run these things in the summer is very different than how they run them in the winter. And so if you want to catch all of the normal modes, you really do have to get like a year's worth of data at least. Yeah. We still have 4? Okay.
I think we went, as you indicate, on what we'll call a deterministic way of doing things like software and everything, mimicking what a neural mind the networks are. But the neural networks themselves are, democratic, statistical. They're bound to make mistakes and so on. So are we, by mimicking that, just creating that environment of actually creating mistakes, vulnerability, and all that, just like we human beings do?
Yeah, they clearly will make mistakes, and you'll find a lot of times people. Article was I reading this morning where, it was something where they were actually trying to use Alexa with its always-on microphones to identify what's going on in the home based on sounds, and they were able to train it, and they said, yeah, we can now identify what's going on in the home better than human beings. Well, it turned out human beings are only like 80% accurate at being able to recognize sounds anyway, so the fact that they were 82% still said they were wrong almost, a fifth of the time. So, getting these things for some of these applications, you really have to be, in the 3, 5, 9 kind of range of accuracy in order, and that remains to be a challenge in a lot of these kinds of problems. Absolutely. Yeah. Question on quantum computing. Well, I think clearly there's some interesting applications of quantum computing in this space, and the fact that you can actually basically compute on all possible states at the same time. I think there is some potential there, and I think there's a lot of research in that area, but nothing that has come out of the labs yet. But I'm quite confident. Well, I know that Google and others have a lot of research going on and how they could leverage that capability. Yeah.
In the case where you're training the turbine, if that anomaly happened where the blade overheated and about to break, and that's never occurred before, how do you train for that?
Well, in this case, we used what was called an unsupervised case for. So we don't give it the answers. We just ask it to look at the data, and it then groups events to things that it considers similar events. So, and since we knew during our training time that everything was, quote, normal in the turbine, all of those similar events were considered normal, and we confirmed that with the customer that, yeah, those were all normal. So what it was basically doing is saying, I'm seeing something that doesn't match any of the things I've seen before. And it's now, it turns out sometimes it reports anomalies that are, they changed the oil to a different type of oil than they've ever used before. And it was completely normal, but it was something it hadn't seen before. So not everything that we report as an anomaly is a bad anomaly.